We're into chapter 17 now, and the book identifies it as spontaneity, entropy, and free energy. But in effect, what we're going to do is look at chemical thermodynamics. That's what all those other words mean. And the difficult math that you had this semester was kinetics. I think that's fair to say. Kinetics was a real problem. This one is going to be equally as difficult, but not with math so much as with concepts. Because thermodynamics and particularly this concept of entropy is one that throws students and instructors for a loop just as easily. I'm going to do my best to try to explain what we're talking about. But the whole point of thermodynamics, at least as far as we're concerned, is to decide whether or not a reaction is spontaneous, whether it will go on its own from reactants to products. Now, this particular, you've seen this drawing before, of course, this graph, where this is energy. And this is the progress of the reaction. And let's say we start off here and we add energy to it to get the activation energy, and then we get down to products. Okay, so we got products here, we got reactants here. And we know that it takes a certain amount of energy, here to make the reaction go, the activation energy. And we also know that from this graph that what we've got here is a difference between here and here is our enthalpy, which in this case will be negative because, right, products minus reactants makes this bigger than that. So this is negative, and that means it's exothermic as written. And if we were it the other way, if we started here and went up there and then down here, we'd have endothermic reaction. So that's what we know about it so far. The point I want to make is that if we divide this graph into sections, and I think I've talked about this before, because when we were in the chapter on kinetics, right, we were interested in this central part right here. The amount of activation energy required for a reaction influences the speed of the reaction. Right? So remember, if we add a catalyst, right, it goes like that. It takes less energy. So the speed of the reaction, the kinetics is in here, and these two sections right here together are talking about equilibrium. And for our purposes, this is where thermodynamics is studied. Is reactants, products, it doesn't matter how fast it gets there. So in a sense, what we're saying is thermodynamics is studying state functions. Right? We don't care about the path. Right? The path has to do with kinetics because a catalyst gives you an alternate path for the reaction that is at a lower energy. But thermodynamics is discussing the state, what it is now here, what it is here, how it got there doesn't matter. For instance, diamond, we think diamond is a very, very stable form of carbon. That's what we tend to think because it's, once you got a diamond, it's forever, so to speak, at least in terms of human lifetimes. But thermodynamically speaking, diamond is unstable. And the reaction of the carbon in diamond with oxygen in the atmosphere is thermodynamically favorable to produce carbon dioxide. Right? It will degrade spontaneously. The difference is that this part in here says it'll take 1 million years to do it. Right? But thermodynamically speaking, the reaction carbon will degrade over time. That's what we call a spontaneous reaction. So we have to get that mindset, right? There's a difference between spontaneous and speed. Okay. So while thermodynamics lets us predict the direction of the reaction, in other words, in this direction, if we say it's spontaneous from reactants to products, then in the reverse direction, it's non-spontaneous. Or vice versa. I mean, if we say from left to right is non-spontaneous, then we know automatically that the reverse reaction is spontaneous. Okay. And I'm just assuming that everybody understands spontaneous means that we don't have to do anything. Just put the reactants together and they go. All right. So let's consider this scenario. We have a gas in 2.4 moles of gas in a 4-liter bulb. 2.4 moles of gas in a 4-liter bulb, okay, at 32 degrees. Okay, and it's connected by a valve to another flask that I believe is much bigger, 20 liters. It's big. And this one is a vacuum. All right. So, and we assume that the temperatures are the same. And throughout the experiment, the temperature remains constant. So the reason we're doing that is because we want to be able to say that there's no heat transfer anywhere, because heat always moves from a high temperature to a low temperature. But if the temperature is the same throughout, right, there's no transfer of heat. So intuitively, you know what would happen when we open that valve, right? All the gas is going to go until we equalize the pressure, right? And when we studied gas laws, we weren't worried with why it happens, right? I mean, we did talk about a theory that explained some of it, but the gas laws allowed us to calculate the equilibrium pressure in those two. Right? We just use, well, in the example we had during gas laws, we had a gas in here and a gas in here, right? Remember, we split them into two and said, okay, what would happen if one's a vacuum? Then we calculate that pressure. What happened if the other is a vacuum? Calculate that pressure, and then put the two together using the law of partial pressures. But in this case, we've only got one vacuum here, and we can say pressure before, pressure after, volume before, volume after, and we can just use Boyle's law and calculate. But now we want to get at, why does it move? What should happen to the gas when we open the valve? Of course, it's going to move to the vacuum. So before we can go any further, we've got to define some terms. Right? We know this one. Right? That's enthalpy. And I think when we covered calorimetry in the first semester, I made a distinction between Q and delta H, because this is heat. This is measurable heat movement, right? Heat flow. And we know that these two values are different if with a gas, the pressure changes. If the pressure is constant and we let the volume change at constant pressure, then these two values are equal. Okay. So This refers to an actual measured amount, and this refers to a potential for a chemical reaction or a process. We also want to add another term. Delta E is a change in the internal energy. And that just means all the potential energy, all the kinetic energy that's contained in a system. And this is also equal to, I might as well put it up here, after I define this one, W is work. So we define all these terms are defined in terms of the system. Remember when we talked about right, system is here and everything else is surroundings. And then we usually isolate the surroundings so we can actually do some calculations. Otherwise, you've got to say surroundings is the rest of the universe. And that's going to be kind of hard to calculate things with that one. So we isolate both of them like that. Now, anything that happens is relative to the system. So if heat moves out, right, then it's going to be a negative value because the system is losing heat, and vice versa. Q would be positive. Same thing for work, right? If the system is expanding against the surroundings, it's doing work on the surroundings, right? So that means work is going out and it's a negative. And if the surroundings are compressing the system, then work is being done on the system, and that's positive. Okay, so internal energy can also be expressed as the summation of heat flow in or out and work done on the system in either way, in or out. So delta E equals Q plus W. And enthalpy in terms of gas is equal to the internal energy plus any changes in pressure volume. Okay, I think I've got all my terms up here. So now we can look at this problem in terms of those values. All right, so for this system, I guess I have to erase this to make room. What would be the value for each of these? Let's put them in the order they're given there. Enthalpy, internal energy, Q, and W. Now we're not given, I don't think we're given enough information to actually calculate values, but we can say whether they're positive or negative or zero. We can definitely do that. All right, so if the temperature is the same from the beginning to the end, then there's no heat flow. There's no heat movement anywhere. That means this is zero. And now the next part is a little iffier because the pressure does change. But for our purposes, this is the system and it's not working against anything. Right? So it's not even doing any work and no work is being done on it. And for all intents and purposes, the delta H is equal to Q in this case. Because actually this system is isolated. Right? It has no interaction with the surroundings whatsoever. So what happens to delta E? Well, if both of these are zero, then delta E has to be zero. Right? Q plus W. All right. Now that we've decided that all of these values are zero, we can't blame the movement of the gas on any one of these because they're not changing. Right? So what's making the gas move? Well, as it turns out, that was a problem at the beginning of the 20th century that scientists were struggling with, including Kelvin, right? Lord Kelvin and his temperature scale. He was working on thermodynamics when he came up with that temperature scale. So constant temperature process means delta H is 0, delta E is 0. It's also, there's no work being done because the gas is working against 0 pressure. It's moving and there's nothing fighting it. There's no pushback. Right? And Q has to be 0 also. All right, so what is the driving force? Well, as it turns out, up to this point, we don't have a clue. Right? Scientists didn't have a clue until a new term was created by Rudolf Clausius at the end of the 19th century. Let's see, he was in Europe, so he didn't have to worry about the Civil War. 1865. He introduced the concept of entropy. And I think I got a picture of him on the next slide. There he is. Oops, come on. There you go. There's Rudolph. He looks like he's mad at the world, doesn't he? I think photographs of that era were like that. They were all like that. I've got old photographs of my grandparents way back when, my great-grandparents actually. And what's happened is the photographic plates were so slow, so to speak, it takes a long time to expose them, that they insisted that their subjects freeze, right? And that's how they froze. But Rudolf Clausius came up with this term, and there were a lot of scientists interested in answering that same question. What's causing the movement? What's causing the reaction? Now, this is just a physical example, but it works also for chemistry. What is driving the reaction? So if we look at this as an example, a picture of what we were trying to describe, what you notice is that on the at the beginning, you've got a vacuum on one side and you've got the left-hand ideal gas filled with a certain number of molecules. When you open the valve, those molecules move into the vacuum and you've got the same number of molecules before and after. There's been no change. This is not a chemical reaction. What you will notice is that those molecules have more room. They got more elbow room, right? And that leads us to a basic understanding of what is meant by entropy. Sometimes, but the simplest way to look at entropy in the beginning, when you're first introduced to the topic, the simplest way to understand it is in terms of disorder. The more disordered, the higher the entropy. And that works up to a point. Right? Then we have to actually get down in the weeds and say what entropy really is. But at least for now, an increase in disorder is an increase in entropy. No. Well, entropy does have something to do with it, yes. Right, because if you've got a membrane and it only passes water, then if you have a more concentrated solution in the say this is the example we always use. It was this long tube and then a bulb and then a flange and then a membrane across that flange, and then you have your hypertonic solution in here, that is higher dissolved solids of some kind, salt or sugar or whatever. And then over here you have pure water. Right? So we know that the water is going to move through the membrane. And we've described it in terms of the kinetic molecular theory. Right? Because On this side, you have more impacts of water against the membrane than you do on this side because there's solutes in the way. And there are things holding the water back on this side. So the equilibrium establishes moving this direction first for water until you build up a pressure. And then the pressure has a greater force on the water molecules on this side, and then you eventually reach an equilibrium. That's one way to explain it. The other way to explain it is what you're thinking of, disorder, right? Water is more ordered on this side because it doesn't have any solute in it. So it wants to expand into this space because that will give it more room. Okay. That's another way to look at it. Okay. So if we look at it in this way, the driving force for a spontaneous process is an increase in entropy. And we specifically say an increase in entropy for the universe. This can either be if the entropy changes for the universe. In fact, that's the second law of thermodynamics. For the real universe, the whole universe, that is everything we know about. This is always greater than zero. What we're interested in is total entropy. And that's for that isolated system surroundings. And if it's greater than zero, then we're saying the process is spontaneous. And if it's less than zero, we're saying it's non-spontaneous. So if we allow the disorder to increase, we're looking at a spontaneous process. If the order does not increase, then we're looking at a non-spontaneous process. Now, non-spontaneous processes do occur. In other words, when we think about disorder, you can get a spontaneous process to increase the order of a system. But it does that at the expense of the surroundings. Right? So you're coupling the two together. And which one becomes more disordered determines what direction the other one will go. We're not going to hammer that one right now. And that's just an obvious statement that this concept of disorder is grossly oversimplified as an explanation for entropy. But that's our starting point. What we actually need to develop as far as intuition goes, and for some people, actually calculation of what the disorder is. We need to look at this in terms of statistics. What are the probabilities of moving from reactants to products? What we're looking for is an increase in the number of possible arrangements of the molecules, or we're going to define this also in terms of energy. Right, so you can have and what we're looking at is this term called microstate. And what we mean by that is it has a unique, each microstate has a unique arrangement of particles and composition of energy. And the greater the number of microstates that are available to the system as it moves from one state to another state, the probability is higher that it will occupy the situation with the greatest number of microstates available to it. I think I've got an example on the next one. Yep. So let's simplify it just as far as we can. Let's see, do I have any more in this slide? Yeah. The microstate is each configuration, right? Those two bulbs is one microstate. And we have 4 molecules available to us. If we have all 4, A, B, C, and D on the left-hand side and none on the right-hand side, that's the only microstate available for that arrangement. Roman numeral 1 is just one possible microstate. If we let one of A, B, C, and D move to the right-hand side, it could either be A or B or C or D. That means we have 4 possibilities. That's more probable than arrangement 1. So arrangement 2 is more probable. If we let 2 move to the right-hand side, now we have the ability to create 6 microstates out of those 4 particles. That means the third proposition has more microstates, it's more probable. Okay. And then we go the other direction. I mean, work our way down. Now we've only got 1 on the left and 3 on the right. It's 4 again. And then all on the right would be 1. So the most probable situation is the one where you have 2 on the left and 2 on the right. And these microstates, the unique configurations, are the largest number of possible microstates determines the outcome. Now, when we're actually dealing with a physical reality or a chemical reaction, the number of microstates skyrockets, right? It's massive, it's huge, because there's so many particles involved. In just a small sample of gas, you got billions of atoms and molecules. So now we're going to discuss this in terms of, we're going to split entropy into 2 propositions. One is positional entropy, and that's the one that's probably been rattling around in your brain since I first introduced this idea. But we also want to look at entropy in terms of energy. Okay. So positional entropy is simply the physical distribution of particles in a system. How many microstates, how many possible positional states are available to solid, liquid, gas is our example. Well, solid has the particles relatively fixed in their positions, right? So those particles can't move. And that only gives them just a handful of possible microstates, right? Because the particles can do things while they're sitting there, right? You know, they can vibrate, they can rotate some in their positions, but they're very limited, right? So solid positional entropy for a solid is very small. For a liquid, it increases because now the particles, the molecules, can move past one another. So we can envision many more microstates available to a liquid. So its entropy increases. And then when we transition to the gas, one thing, if we've got the same number of particles and the pressure hasn't changed, then the gases are going to expand. It's going to occupy more volume. And that gives it a huge number of possible microstates available to the to each proposition. So in terms of position, the entropy for a gas is much, much greater than liquid, which is also greater than a solid. Right? That's probably the easiest one to understand. So next we want to look at energy entropy. think of energy entropy in terms of, are we increasing the total energy in the system and surroundings? Or if we can isolate the systems from the surroundings or discuss them independently, let's do that. Say we have a system and we have an endothermic process where energy is entering the system. Then we're increasing the energy entropy of that system. And consequently, the surroundings are decreasing their energy entropy because they're losing energy. And what that means is that the particles are slowing down. So if the entropy decreases for the surroundings, then the particles are slowing down. They're not finding themselves in unique microstates as often as they were before. And this slide is saying, think of it in terms of energy randomness. And that's up to you. Sometimes I do and sometimes I don't think of it in those terms. I think of it in terms of envisioning the particles. And when we add energy to them, now they're moving faster. They can get anywhere they want quicker. And they can occupy more possible microstates as a consequence of that increased energy. All right. So let's take a practical approach here and just look at overall change in entropy for the following situations. And if delta S increases, we're saying the value is going to be positive. That means an increase in entropy, right? Okay, so how about evaporation of alcohol? Right, what happens to the alcohol? It goes from a liquid to a gas, right? So it has a positive delta S. Should have a positive delta S. Oh, that box at the top, that's just information. I said there were a lot of people working on this problem along with Clausius, or shortly after Clausius, he introduced the concept. And one of those was Boltzmann, who was a master mathematician. And his proposal was that entropy could be calculated if we knew the number of possible microstates available to the system. That's what that big W is. And then K is a proportionality constant, Boltzmann's constant. Now, don't ask me how they calculate the number of possible microstates. That's completely beyond me. This is one of those equations which accurately describes the law, but is unwieldy as given. We have to make a transformation to some other form, mathematical form, before it becomes useful. Okay, now back to our problems. How about the freezing of water? It goes from a liquid to a solid. The entropy should decrease, right? Because the solid is more ordered. If we compress an ideal gas at constant temperature, right, we're reducing its number of possible spaces, its microstates decrease, so its entropy ought to decrease. If we heat an ideal gas at constant pressure, what's going to happen? We know that if we heat a gas, we add temperature, then the volume is going to change, right? That's Charles' law. So it's going to expand, and that gives it more possible microstates. Also, we're adding energy. So we're increasing the energy entropy as well. So that's an increase. And if we dissolve sodium chloride in water, what happens to the entropy of the sodium chloride? Well, we start off with sodium chloride in a solid. Now we've got the ions separated from one another in more possible microstates. So that should increase the entropy of the sodium chloride. All right. Thermodynamic laws, just as a refresher. The first law of thermodynamics says that all the energy in the universe is all the energy it's ever had, all the energy it's going to have. So this term, change in energy for the universe, is always zero. Can't create it, can't destroy it, it doesn't change. Started off with that much, we ended with that much. The second law introduces the concept of entropy. And that says that the change in entropy for the universe, and that we do mean the universe here, the whole universe, is always greater than zero. And in any spontaneous process, there's always an increase in entropy for the total. So if we're saying the process is spontaneous, say we conduct a chemical reaction and we let it go, and it spontaneously goes from reactants to products, then we know that the total entropy for the system and surroundings is greater than zero. Okay. The authors of the textbook tend to conflate the use of delta S universe and delta S total. I want to make a distinction. The delta S universe, for me, is the universe. That's everything there is. Delta S total is what we're actually aiming for. Right, and that's what that statement's all about. In order to do that, though, we have to isolate the system and surroundings from the rest of the universe. All right. And another way of expressing this is to say that the delta S total is going to be the change in entropy for the system plus the change in entropy for the surroundings. Okay. So if we can quantify these two terms, we can determine whether this one is positive or negative, and determine if the process is spontaneous in the forward direction. Okay. I already mentioned this, but I will make another comment here. If we determine that this value, total entropy for the system and surroundings together, this isolated system surroundings, is zero, that means the system is this whole system surroundings is in equilibrium. There's no change, right? If delta S total is zero, that means the system and surroundings are not changing, and that signifies equilibrium. All right. Let me see. Let's see. I'll better erase this and make room. I'll leave that there for now. Okay, say we have A as a liquid and A as a solid. From left to right, we're going from liquid to solid. Which direction involves an increase in energy and randomness and positional randomness? Well, one thing we can say for sure is that when you go from a liquid to a solid, the solid is more stable, and you're giving up energy in order to do that. Right? We know that when water freezes into a solid, we extract energy from it in order to do that. So it's an exothermic process. That means that the delta H goes on this side. Right? For exothermic processes, I put enthalpy as a product. Okay. So that means this has lower energy entropy than this side. How about positional entropy? Let's see. Energy entropy, energy entropy. Let's write it this way. We have energy entropy from this side. Energy for A, for the liquid, excuse me, for the liquid. And energy entropy for the solid, right? And the entropy is decreasing as we go that way. So this energy entropy is less because we've extracted some energy from it. How about positional entropy? Positional entropy for the liquid versus positional entropy for the solid. Well, the entropy here should be less. Yeah, energy randomness favors the formation of solid, decreasing from liquid to solid. Okay, I'll agree with that. Positional entropy decreases from liquid to solid, reducing the number of microstates. Right, so we're also less on this side. So we have to look at the balance between the two. All right. Now here's where the concepts get a little difficult. I'm going to try to draw an analogy. As temperature increases or decreases, which one of these positional or energy entropy, which one takes precedence? Let's look at it in terms of energy. So if we increase the temperature, we're increasing the temperature. Then what impact does a change in temperature at any one of these relative positions have on the overall entropy? Think of it in terms of percentage. Say I am in my current financial state, you know, dirt poor. And I meet you on the street, right? You're not my student anymore, so we can't say it's bribery. And you offer me a $10. Now offer me $100. That'd be better. So you're going to give me $100. What impact would that have on my budget? If I'm poor, say low temperature, low income, right? You offer me $100, it has a great impact on my budget down at this level. But if I'm a millionaire and you offer me $100, I'm up here, and that $100 has very little impact on my budget. So that's the analogy I'm trying to use. So at higher temperatures, the energy entropy is less of a determinant in the overall entropy for the system. So if at high temperatures, let's see, on this side we have energy entropy. Energy entropy influence. How about that? Influence of energy entropy on the total is greater as you decrease temperature and less as you increase temperature. So the balance then shifts in this direction. It shifts toward energy entropy and away from positional entropy. Let's get that out of the way. This would be influence of positional entropy is greater as the temperature increases because this one decreases. Okay, that's what I'm trying to say. Now that's the way we look at it in terms of what is the influence of positional entropy. But we can also focus on positional entropy by itself. As we increase the temperature, things are moving faster. So there are more positions occupied in the same amount of time at higher temperatures than at lower temperatures. So you're actually increasing the positional entropy component as you increase the temperature because things are moving faster. All right. At what temperature is there a balance between the two? That's at a phase change. Now we're talking about purely physical. So at the phase change, these two are in balance. If we could quantify these two, they would be exactly equal at phase change. So when you're going from liquid to solid or solid to liquid, if you're going from a gas to a liquid or liquid to a gas, then these two are equal. And we observe that with our plot of phase changes. Remember, we're increasing temperature from left to right. And this is just phases, right? So if we have a solid, we're heating a solid, right? And then once we get to the point where we got solid and liquid together, temperature stops moving. It stays the same. And then once you got rid of all the solid, now you got liquid, it heats up some more. Right? And this is just liquid. And then when you got liquid and gas together, then the temperature stops changing again. Because at these points, these two are equal. And then once you've got all gas, then you can heat it up some more. Okay. Let's see. Describe the following as spontaneous, non-spontaneous, cannot tell. All right. This one, it's difficult to find a good place for this slide. Because if we had already discussed the topic of free energy and the equation that goes with it, then the discussion here would be a lot easier. But what we're going to try to do is, develop an intuition here for whether or not the reaction is spontaneous. If we're balancing energy entropy and positional entropy. So the first one is where we have an exothermic reaction. That means delta H is negative. And the system becomes more positionally random. So delta S is positive. Okay, that's what that tells us. All right. So look at each one in terms of which is favorable. Well, we know this one's favorable because it's positive. And we're going to say this one is favorable because why? Because reactions tend to go when the products have less energy than the reactants. That means they're more stable. Exothermic reaction means the products are more stable than the reactants. So that's why we're saying this one, this exothermic process is favorable. If both of them are favorable, then we're saying that this particular reaction is spontaneous. All right. Suppose we're exothermic, and this one is more ordered, less positionally random. In this case, we can't tell because this is favorable and this one is not favorable. So it depends on the balance between the two, right? If this one is low and it's not favorable character, and this one is high and it's favorable character, then it should be spontaneous. But we can't tell. Okay. That's the problem. What if we flip it? Now we go endothermic and more positionally random. Endothermic means delta H now is positive. And delta S is also positive. Right? So this one is favorable. This one is non-favorable. For the same reasons that this one is favorable, exothermic is favorable, endothermic is not favorable. Because now the products have more energy stored in them than the reactants. We can't tell because we don't know the balance. Okay, then the last possible process is endothermic and less positionally random. So now we have endothermic. Oops, didn't mean to do that. There. And less positionally random. That's negative. In this case, they're both not favorable. Okay, so that means this is non-spontaneous. Right? All right, what else can we say about this? Not spontaneous, unfavorable for both, yep. We're also saying that this one and this one are not temperature dependent. Okay, this one is a no-brainer. This one's not temperature dependent because they're both favorable. So it doesn't matter what the temperature is. Right? But how about this one? If they're both not favorable, well, that should have, right? For the same reasons that this one is favorable, favorable, non-favorable, non-favorable, then they're both independent of temperature. It doesn't matter what the temperature is. They're both non-favorable in any event. Whereas B and C, right, that's the only other option. B and C depend on temperature. These two are temperature dependent. And that fact right there is why we get a better understanding of this A, B, C, and D when we discuss free energy. And I'll point that out to you when we get to free energy. All right. Now let's look at system surroundings. I get that. Okay. Let's look at system and surroundings. And we'll see. So work. I'll put WD-40 on it before you guys got here. Helps it a little bit. Until I rub all the WD-40 out. I'm gonna erase this. Put it back if we need it. Let's look at, let's see, we have our system here, we have surroundings here, and they're isolated. That. We want to focus on delta S for surroundings. Okay. The sign of delta S depends on the direction of the heat flow. So if the heat is flowing out of the system, if heat's flowing out of the system, relative to the system, that's a negative value. But what's happening to the energy entropy here? It's increasing, right? So if heat is flowing out of the system into the surroundings, then the delta S should be increasing for this scenario, right? It should be positive. So we can also say that what's the right word? The equivalence of Q and delta H, we're assuming for now. So that means if delta H is negative, then delta S surroundings is positive. Okay. And of course, vice versa. If delta, I might as well put it up here. Let's be complete. If delta H is positive in the other direction, then delta S surroundings should be negative. Okay, so far so good. The magnitude of this change is temperature dependent. We talked about that earlier when I gave you the analogy of rich man, poor man. At high temperature, the effective temperature is lower. So that means the change in the surroundings is inversely proportional to temperature. That is, as temperature gets bigger, the effect on delta S surroundings is lower. And vice versa. Okay. So what we're saying is that mathematically speaking, delta S surroundings is proportional to enthalpy change, directly proportional to enthalpy change, and inversely proportional to Kelvin temperature. Okay. And if we choose our units correctly, we can also say this. That, except for one problem. Except for one problem. Right? If this one is negative, that one's always positive, so it's no brainer. Then how do we get this one to be positive? If that one's negative, how is this one positive? Right? Because we've got to fudge it to make the units come out correctly. You know, their signs be correct. So what we have to do is introduce a negative here. Right? We sort of painted ourselves into a corner. Now we need a way to get out. So since this is negative and that negative by this, now this is positive. And that works. So that's our first useful equation. So for an exothermic process, delta S for the surroundings is positive. And if we make this delta H positive, right? And times that negative, then delta S surroundings is now going to be negative. So this is another way to look at when I mentioned exothermic is favorable and endothermic is not favorable. Exothermic gives us positive surroundings. Endothermic gives us negative surroundings. So that implies favorability or not favorability for the second possibility. All right, so there's our first useful equation. Excuse me, I'm going to put it over here. So delta S surroundings equals negative delta H over T. And we're going to add equations as we develop them. And this has to be constant pressure, we're gonna stipulate for this one. That only works at constant pressure. Now, if we want to say this, we could also say this, negative Q. If we're going to measure the heat flow, then negative Q over T would work no matter what the pressure was. But delta H only works if the pressure is constant. Most experiments, for that reason, most experiments are conducted at constant pressure. If at all possible. That way, the measurement here gives you access to the enthalpy. All right, and that's what this slide is all about. Enthalpy is a thermodynamic potential, similar to internal energy, and they're state functions. And we also define enthalpy. I think, no, we didn't do this one. Yeah, I think we did put this one on the board. So if we go, let's see, I need some space, so I'm going to have to erase this. We defined enthalpy in terms of internal energy. There's internal energy change. These are always delta or change values. We don't work in absolutes. And then whatever happens to the gas in terms of change in pressure and volume. Right? And when we talked about calorimetry last semester, I showed you the equivalence of this as a work function and force times distance is actually work. But when you're considering an expanding gas or a contracting gas, then pressure volume is more useful. Right. We've already worked out that equivalence last semester. Okay, so what is delta E equal to? We did delta E is equal to Q plus W. So heat transfer plus work done is delta E. So if we say substitute that in here, we have Q plus W plus B. That should be next. Okay. If the process takes place at constant pressure, then we can pull that pressure term outside. It doesn't change anymore. We're letting volume change. So that's what we're up to next. Now, work, and we did this one when we were talking about calorimetry also. Work is negative P times delta V. Negative pressure times change in volume. All right, so I'm dredging that up from last semester. Now, if we substitute that for work, right, now we have Q minus P delta V plus P delta V is equal to delta H. So at constant pressure, these two terms cancel. And that's how we have enthalpy equal to Q, only at constant pressure. All right. So now, is this messing with your head yet? Yeah. I'd be surprised if it wasn't. Just keep the prize in mind, right? What we're trying to do is determine whether a reaction is spontaneous. And eventually we'll be able to determine how spontaneous, right? We've actually put values in those positions so that we can quantify the spontaneity of a reaction. Okay. So if we have this summation here, delta S total equals delta S for the system plus delta S for the surroundings. Then if we can say system and surroundings are both positive, that means this one has to be positive. Right? That's the first possibility. This means spontaneous, automatic. What if they're all negative? Right? Then this one's negative. That's non-spontaneous. Right? What if system is positive and surroundings negative? Well, then we don't know. It depends on which one's bigger. If surroundings entropy change is bigger than systems positive change, then we get no reaction. Or if we flip it the other way, right? Similarly, we don't know. Right? We have to have those values, absolute values, in order to determine whether the total is positive and gives us a spontaneous reaction or process. Okay. All right. Now we're gonna let Josiah Willard Gibbs talk. Gibbs' interest centered around useful work. Right. These processes, and this is at the end of the 19th century. These processes were being investigated not just for pure science. I mean, there were people that stood to make a lot of money if we could extract energy from a process and make it do work. We're talking about the Industrial Revolution. That's what's going on here. So a lot of this work was done in England, France, Germany, where fossil fuels had been discovered and they were being put to use, right? The steam engine, for instance, right? How to make the steam engine more efficient, right? People like Lord Kelvin were working on this. People like Sadi Carnot in France, who eventually solved the problem for a practical engineering standpoint. And then others who actually created the engines. But it was all based upon thermodynamic work. And Gibbs produced this equation that quantified how much free energy or energy that's available to do work can you get from a reaction. And that's why it's delta G in honor of Gibbs. Once you know the enthalpy, the potential, the thermodynamic potential, then you subtract this term, the entropy term, right? That's the energy that's lost to a change in entropy. Okay. So what does that mean? Well, this is going to be joules, right? This is going to be joules. We could say per mole, but I'm going to leave the moles out. And this would be joules per, not degree, joules per K. Because this is in K, K's cancel, leave us with joules. Okay. All right. So this equation allows us to determine how much energy is available to do work. Oh, by the way, put that note in there. Whenever delta S, or whenever any of these terms doesn't have a subscript, we mean system. Just assume it's a system. All right. Next, what we want to do is we're going to rearrange the equation. First, we're going to divide the whole thing through by negative T. Right, negative T. Negative T. We can do that, can't we? Right. Algebraically speaking, if we divide the whole thing through by the same value, then we haven't changed the equation. Okay, so what does that give us? Well, that gives us a negative delta G over T equals a negative delta H over T. And in this side, the negative makes that a positive and the T's cancel. Okay, so that's where we're at right now. Okay, we've also got this possibility here, delta S surroundings minus delta H over T. So if we say, surrounding systems, okay. We're also going to say that if this is system, let me separate it out here. Remember what we said, S total, delta S total equals delta S system plus delta S surroundings. Okay, so notice that this looks like we've got system here, right? So this should be delta S surroundings, and it is. Right? So we end up with negative delta G over T equals the delta S for surroundings plus the delta S for the system. Like that. Because this is equal to that right there. And I'm gonna keep this one for now. We can throw it away later if we want. So what does that mean? That means if A is equal to B and B is equal to C, then A is equal to C. That means delta S total is actually equal to negative delta G divided by Kelvin temperature. Okay. So what does that mean in practical terms? Well, we know that if delta S total is greater than 0, we have a spontaneous process. Right? So if this is positive, what does that say about delta G? Because temperature is always positive. Well, if this is positive, delta G has to be negative. Right? Delta G would have to be negative times that negative to give you a positive for a spontaneous process. So we're also saying that delta G less than 0 is spontaneous. So if we know the free energy, if we can calculate the free energy for a reaction, we can use that, and it's more convenient actually to determine this one than to try to figure out what delta S total is. All right, so let's take this example. A liquid's vaporized at its boiling point, constant pressure. What's the sign on each one of these? A liquid is vaporized at its boiling point. So the gas is doing work on its surroundings as it expands, right? So that should be a negative value, right? Right, because everything's in relative to the system. The vaporized gas is pushing against atmosphere. So that means it's doing work on the atmosphere. The system is losing. So that's negative. What about heat? Well, heat's being transferred into the system to vaporize the gas. So that value should be positive. And if it's at constant pressure, which it is, then delta H is also positive. Okay. What about the entropy change of the system? Well, the system is going from liquid to vapor, right? So the gas is more disordered, entropy of the system is increasing. How about the surroundings? right? As heat enters the system, surroundings become more ordered. Right? We're extracting energy entropy from the surroundings to heat the gas. So the surroundings should be negative entropy change. How about delta G? At the boiling point, the system is at equilibrium. So there's no free energy available. Delta G is 0. Another way to look at that is well, no, the best way to look at it is to understand that delta G is 0 at the phase change, at this boiling point. So if we do that, then, and we look at this equation now without all the manipulations, go back to this equation right here. Then if delta G is 0, that means delta H is equal to T delta S. Right? I just moved this one on the other side and flipped them around. Okay. All right. Make some more room here. Let's see. We had an equation here that I should not have erased. Here it is. That may not be so useful though. Let's go back. That one might be useful. Delta H equals T delta S at equilibrium. That. Trying to savor useful equations here. Let's erase this one. We'll do it on that. I know it's coming up on one. We're good till 12, aren't we? Always have to keep reminding myself. 12:20. Okay. All right, so let's go to the next slide again. The value of delta H of vaporization, the enthalpy of vaporization of a substance, X is 45.7 kilojoules per mole. 45.7 kilojoules per mole. If X, this is delta H, vaporization. So that means X as a liquid is going to X as a gas. That's what they're saying. And its normal boiling point is 72.5 degrees. So boiling point, normal boiling point, which means standard conditions, 1 atmosphere pressure, equals 72.5. Yeah, 72.5 degrees C. All right, calculate the delta S for the system, surroundings, and delta G for the vaporization of 1 mole. All right, so we've already said at the boiling point, delta G is 0. Right, there's no free energy available. The delta S for the surroundings is minus delta H divided by T. Right. So, and what you'll notice also when we do calculations is that delta H is often given in kilojoules and delta G is often given in kilojoules, but delta S is always given in joules per K. So watch those units of measure. So that's why when we calculate delta S for the surroundings, we want negative 45.7 times 10 to the third joules. And the temperature is 72.5 plus 273. Okay. So when we do that calculation, we get minus 132 joules per k mole. Minus 135. Yeah, joules per k mole. That's delta S surroundings. Now, at equilibrium, the entropy change for the surroundings is equal but opposite in sign to the delta S for the system. That means it's going to be a positive 135 joules per k mole. Okay. And the reason for that is it's not spontaneous. I mean, it goes neither direction. Delta S total is 0. So you just have to change the sign. All right, there we go. So we could also write this. Delta S for the system equals delta H over T. And this is for an equilibrium situation also, if that's the case. Oh, Professor Dave is going to talk.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around, entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T, so entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the non-polar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water soluble due to the polar heads facing out. That's how soap works, and that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy storing processes. In this way, systems can defy entropy on the small scale. But the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
a real toe tapper. Okay. Is he done? He's done. Let's see if I had a font. It's gone. Moving on. All right. So we have oh, now I remember. Sometimes it's helpful to get somebody else to explain this to you, right? Rather than just hearing it from one person or from one book. And if you want, I think Khan Academy has a pretty good explanation of some of these ideas. Okay. So these are the various possibilities, combinations of enthalpy and entropy show that the processes are either independent or dependent upon temperature. So this is where I wish we had understood this before we tried to do that previous slide where we were saying exothermic and more disordered, or endothermic and less disordered, right? This equation solves that problem for us, and the implication of spontaneity versus temperature. So if we take this equation, we know that in order to be spontaneous, delta G has to be negative. So what happens if delta S is positive and delta H is negative? Right? This is spontaneous. Any temperature. Temperature doesn't matter. If that's positive, positive times a negative plus a negative is a negative. So temperature doesn't matter for that situation. If they're both positive, right, when would this one be negative? This one would be negative at high temperature, because that would make this value much larger than that one. So this is spontaneous at high temperature. Let's see. And if they're both negative, right, that term is negative, this term is negative, then this negative times that negative means positive. So a positive against a negative means if we want this one to be negative, then the temperature must be low to make this overall term positive very small. So only at low temperature would this be a spontaneous situation. Okay, and the last one, negative and positive. So if we have negative here and a positive here, then negative times a negative plus positive is positive. This is non-spontaneous at any temperature. Temperature doesn't matter. Okay. Now we're going to get down in the weeds here for a minute. Got this situation where gas A, diatomic gas A, reacts with diatomic gas B to produce, and I guess it's equilibrium, produces this gas, AB gas. So if you looked at them in terms of their bond, there would be a bond between these two, there'd be a bond between these two, and there would be two of these with a bond between the A and the B. that beware in the red is so that we don't go off in the wrong direction. What does bond energy mean? We want the bond energy of AB is greater than that of either of the reactants. If the bond energy here, energy for the bond here for AB is greater than either one of these. And I'm not going to put AA or BB there because it doesn't matter. It's greater than either one of those. What does that mean? Bond energy means it's the amount of energy you have to add to break the bond. Right? So that means the overall energy of this one is lower than that one because you have to add more energy to it to break the bond. All right. This one is at a lower energy state. Let me write that in here. Lower energy state. Because the bond energy is higher. And this is at a higher energy state. Okay, now let's answer these questions. Predict the sign of delta H, delta S surroundings, delta S system, and delta S total. Well, if we look at, remember how we calculated the delta H when we knew the bond energies. If the delta H equals the sum, that's wrong. I need a sigma. The sum of the energies for the bonds broken. So that means this side. Right, so this would be the energies for reactants minus the energies for product. And bond energies are always positive, right? Because you have to add energy to each one to break them. So if these are at a higher energy state here, and this is at a lower energy state here, then delta H should be positive, correct? Oh, why is it saying negative? Predict the sign. Am I looking at this backwards? Bonds broken. Oh. My mistake. Yeah, that is negative. Let me correct myself. I just fell into my own trap. This is the bond energy. That's what this is working on here, bond energy. So the energy required here is greater. That's bigger. This is smaller. Delta H is negative. All right, how about delta S for surroundings? Well, in that case, we can use this equation. If that's negative, and times a negative, then the delta S for the surroundings has to be positive. Correct? That is correct. How about the delta S for the system? Well, we're not sure. Right? What happens to the delta S for the system? We're assuming that it's approximately 0. Right? In which case the delta S for the surroundings, the total would be positive. All right. Professor Dave mentioned the third law of thermodynamics, and I just put this on here for general interest. Because what we're saying is that at absolute 0, the entropy of a perfect crystal is 0. That's our 0 point. So what that means is if we are able to calculate the entropy change for any other reactant or product, they all have positive values because they're coming from 0. See, it's not like enthalpy, where we take 0 point as the most stable form of the element or compound at standard temperature and pressure. Right. So for enthalpy, that would have delta H of 0. That's its most common stable form. Right. For elements. Compounds, then you can calculate, but it's a different entropy is a different mindset. We're starting at 0 from absolute 0. So everything has an entropy term, excuse me. And we can calculate standard entropies the same way we do enthalpies. We just need to know what is their standard entropy for the products and the reactants. So we take the product total entropies, subtract the reactants total entropies, and we can find the entropy change for the reaction. And that little 0 up there at the top, that means standard conditions. And your reaction may not be occurring at standard conditions. Right? So this is only good for standard conditions. Now, if we knew what the entropy values were for the reactants and products at different temperatures and pressures, then we could calculate the actual entropy for the reaction. This statement is true. The more complex the molecule, the higher the entropy value. And the example we're going to use here is the difference between water and hydrogen, dihydrogen. Okay. So what are the possible energy states of the water molecule? Well, you can get bond stretching. It can stretch this way symmetrically like that. And that can be measured. It's usually measured with infrared spectroscopy. Or you could get an asynchronous stretch and contraction like this. Or you could get a change in bond angle. Right? Just go flop like this. It may not be much, but it's measurable. And then the other is the whole thing could rotate. Those are 4 possible energy states for water. How about hydrogen, though? Hydrogen can only stretch or rotate. Right? It can only stretch this way, or it can spin. That's it. So the more complex molecule has more possible microstates than the least complex molecule. All right. So here's a situation where you can calculate the entropy change for this reaction. Sodium plus water yields sodium hydroxide plus hydrogen. Now we know from practical experience that this is a spontaneous reaction. Right? Just throw a chunk of sodium in your neighbor's swimming pool and see how long it takes them to sue you, right? Because it will crack the bottom of their pool. Right? Sodium reacts with water violently. Potassium works better, but if sodium's all you got, then go ahead and use it. So what is the entropy change for this reaction? Well, the absolute entropy value for sodium is 51 joules per k-mole, but we've got 2 moles of it. So 2 times that is 102. Right? Same thing for water, 2 of them. Same thing for sodium hydroxide and hydrogen. You add the sodium hydroxide cumulative value with the hydrogen and subtract the sodium and the water. And we get a value of minus 11 joules per K. Now, this is an absolute value. And that's just for the system, correct? Right? It has no subscript. So we're saying this is for the system. Right? If we were trying to predict spontaneity, we would have to know what the surroundings were so we could get a total value. But we don't have that. So for this slide, it's just an example of the calculation. And there are a bunch of those, excuse me, a bunch of those in your review document to give you some practice. All right. Since we know that delta G0 equals delta H0 minus T delta S, then we can substitute and rearrange, and we find that delta G0 for the reaction can also be calculated the same way. You have a list of delta G values for products and those for reactants, and subtract the two, and you'll get the delta G0 for the reaction. So, say for this example, a stable diatomic molecule spontaneously forms from its atoms. So if we have 2 X's, and this must be a gas because we don't want any other phase changes to influence the energy. Now we get a diatomic molecule from that. Okay. Spontaneously forms. Right. So we know if it's spontaneous, that's under standard conditions, delta G has to be negative. Right. How about delta H? Well, when we got 2 separate atoms, they're at higher energy state than this because the bond lowers the energy of the overall system. So that means we're going to lose heat. Delta H has to be negative also. So how about delta S for the system? Well, if we look at Gibbs, all right, this one's negative. This one's negative. And we're at standard conditions, then a minus times a positive. Right? Because temperature is always positive. So that means delta S has to be positive. In order to give us a spontaneous value, we're assuming. Why are they saying they're all negative? Okay, let me see. Where did I make a mistake? Explanation. Okay. I got the first one right. Delta G is spontaneous, it's negative. Delta H is negative because molecule at lower energy than the separate atoms. That's true. Oh, that was dumb. Delta S in terms of the system, we're going from more random to less random. We're going from 2 moles here to 1 mole there. All right. So that means that this overall term is positive. So under what conditions would this be spontaneous? If that's negative making the positive here, and this has to be negative greater than that, that means temperature would have to be low. All right. So let's see, what do we got here? Consider the following system at equilibrium. All right. I can make sense of this one. All right, we've got PCl3 gas, CL3 gas, plus Cl2 gas produces PCl5 gas. Okay. What will happen to the ratio of partial pressure of PCl5 to partial pressure of PCl3 if the temperature is raised? All right, so we're looking for this ratio of the partial pressure of PCl5 to the pressure of PCl3. Right? Is it going to go up or down? All right. Oh, delta G is negative 92.5. Delta G 0. Let's see. Let's put here. Delta G 0 equals minus 92.5 kilojoules per mole. Now, it's obviously per mole. That's 1 mole, 1 mole, 1 mole. Okay. How do we predict which way this reaction is going to go, left or right? Think of Le Chatelier. What effect does temperature have on a reaction? It depends on whether it's endothermic or exothermic. Where does the delta H go? Right. Does the delta H go on this side or that side? Well, I would predict that if we're taking these two compounds and making a single out of them, that it's going to be an exothermic reaction, more than likely. But since we're in the Gibbs free energy range, let's see if we can use Gibbs equation. Right, to tell us the sign of this value right here. If we can find out what the sign of that value is, we know which side the heat goes on, and then we can use Le Chatelier to tell us, is it going to increase this and decrease that? Right, in which case this would increase. But what happens since this is negative? What is delta S? Delta S is probably negative. We're going from 2 moles here to 1 mole there. That's probably negative. Correct? So, if this is negative and this term is positive, delta H must be negative. It has to be negative in order to make this one negative, because this term now is positive. So now we know that the reaction is exothermic. Delta H goes on that side. So if you increase the temperature, the shift is to the left. That will decrease this value, increase this value, and this one, this ratio decreases as temperature increases. Okay? All right. And there's the explanation in black and white. Okay. We're not done yet. Okay. So for the past 3 or 4 slides, we've looked at the standard conditions. But that really doesn't tell us much, because we can't conduct every reaction at standard conditions. So we need to know, how do we determine the actual delta G? Right? And there are 2 possibilities. Delta G is delta G 0 plus gas constant, and this is 8.3145 joules per, let's see, per mole. Okay. Has to be the one with energy in it, because this is energy unit. And then this temperature times the natural log of the pressure. What's the pressure of the system? Or actually, this one is more useful for us. Delta G0 plus RT log Q. Right, we know how to calculate Q, right? You write the K expression, the equilibrium expression, and put the actual values in there before equilibrium is reached. And that tells you, we used Q in the past to tell us which way the thing would move. But now we're going to use it to inform what's the actual value of delta G. All right, so hold that thought. In terms of chemistry, systems are tending toward the lowest possible free energy by going to some equilibrium position or by going to completion. It depends. For chemical reactions, most chemical reactions tend toward an equilibrium situation where if you start off with a reactant A and you're headed for product C, or if you're coming from the other direction, from a B position to C, then there's a low energy point in the middle. Phase changes tend to go all the way to completion. All right. So at the equilibrium point, then delta G would be 0 right here. This would be 0. Right? So what is this value? If delta G is 0 and we're at equilibrium, that value must be K. Let's see, this is T. Plus delta G 0. And that's equal to 0. Okay, so what we're saying is, if we move this to the other side, solve for delta G 0, it's a negative RT log K. And that's it right there. So this gives us a handle on equilibrium constants relative to the free energy. Now, what does that look like graphically speaking? That's where this is going to grab your brain, sure. Say we have a process where we're going from an A gas to a B gas. And we express the free energy of each one, right? So if we have the free energy of let's see, we're going to use this one. So if this is the free energy of A, then this will be the pressure of A, right? And this would be the standard free energy of A. And so we just put the subscript in here for each one, and we do the same thing for B. Pressure of B. There we go. And we graph them. Right, so on the graph, the actual free energy of A is on the first plate, the A plate. The fraction of A reacting, we're increasing the amount of fraction A that has reacted. That's what we're saying on the x-axis. We're going from 0 to totality. So it looks like that A has reacted, 75% of it has reacted. And its free energy has dropped to a certain value. Then if we look at the product, if we come from the other side, right, in an equilibrium situation like this, if we come from the other side, right, we're on this one, the first plate was this way, the third plate was this way. So if we're coming backwards, from B, its free energy is also decreasing as it moves back toward A. Well, there's a point in there where the free energy of the two is the free energy of A plus B. Right? So G of the total equals G of A plus G of B. And the G of total is supposed to be, once we reach equilibrium, the G total must be equal to 0. That means A has to be equal to B. I think that's the next slide. Whenever B is greater than A or A is greater than B, we have a driving force to meet somewhere in the middle. And that means a lower value of delta G. So when we add them together, delta G must be 0. Right? They have to be, we reach a point where the relative values here are equal to one another, but opposite in sign. That's the best I can do. All right. Let's see, we've got another equation here. Let's put this one over here. Delta G 0 equals minus RT log K. This is at equilibrium. Okay. And I guess we put the other one over here too. The actual delta G is equal to the standard delta G plus RT times log Q. Yeah. Okay, now I can erase these. Okay, so with this equation right here, if we're at equilibrium, then we can say something about the relationship between the standard free energy and K. If delta G 0 is actually 0, then K would have to be 1. Right? Remember what logarithm is. The base of this one is E. So E to what power is 1? 0. E to the 0 power, which is this one. Right? So delta G 0 is 0 when K equals 1. If K is greater than 1, that gives us a positive value here and a negative value there. So when K is greater than 1, delta G is less than 1. Right? That means it's spontaneous for K greater than 1. If K is less than 1, it's the other way around. Now delta G is positive when K is less than 1. And that means it's non-spontaneous. Right, so we can draw that conclusion, not just from delta G 0, but from K. Right? All right. So let's go back to the original concept of Gibbs and free energy. By the way, Gibbs wasn't the only one that produced equations for calculating free energies. There were others. Only Gibbs is the easiest to understand. The others work in special conditions, and I'm not competent to describe them, so we're not going to talk about them, except just to say that they're out there. So this is this actual delta G, not the 0, but the actual delta G of a reaction will tell us the maximum amount of work that can be done with that energy that's available. This is the available free energy, gives us maximum work. Okay. This only happens for reversible processes that can go backwards and forwards. And reversible processes only go when the limit, we say in calculus, the limit of movement forwards and backwards is infinitesimally small, approaches zero. Okay? So the limit here in calculus terms equals zero. The limit of this process approaches zero. That means that the movement is very, very small. That makes it reversible. So this is the maximum amount for a reversible process. All natural processes are irreversible because they don't happen in very small forward and backward increments. That means the actual work obtained from the free energy is always less than the maximum. We lose something in natural processes. Wmax can never be reached. Okay. So let's see. The next topic is a practical application and how we can relate K, equilibrium constant, to temperature. All right. So this is known as the Bandt-Hoff equation. And it's derived from this expression right here, like minus RT log K. Yes. So if we say delta G0 equals negative RT natural log of K, let's see, I better put that in parentheses. And we also have delta G0 equals delta H0 minus T delta S0, right? This is Gibbs equation. This is a derived version. Then if now we take, let's see, now we just take this part here. And we divide both sides by negative RT. So divide by negative RT. What does that get us? Well, this one divides into that one and cancels it. So we have log K on this side and negative RT on this side. So we have delta H0 times R, that's negative, divided by T. And this one, negative divided by negative, is a positive. T's cancel. And we have delta S0 over R. Okay, you see how that happened? So what we're going to do for this one, excuse me, I put R in the wrong place. Right, it's in the denominator. Right, so the denominator goes in like it's RT. There we go. That's much better. Now let's put this in a form y equals mx plus b. Make a straight line out of it. So we have this y, which is, we don't have to touch that. This one, we're going to factor out 1 over t. Because delta H0 for the system would be constant and R is a constant, but temperature will vary. Right? So there's our x and there's our slope, and this is still delta S0 over R. Okay? So if we have a set of experiments, okay, where we change the temperature and measure the K, so we have a set of data with temperature versus K, and we know that K is going to change when we change the temperature, right? That's given. Then what we can do is take the natural log of all of our Ks and the inverse of all of our Ts and plot them. So this is our X, so this is 1/T, and this is Kelvin to the -1, right? And this is going to be K, natural log of K. Then it has a negative slope. So it's going to have a negative slope like that. And the slope is going to be negative delta H(0)/R. And the y-intercept is going to be delta S(0)/R. Okay, so if you do several experiments and plot that data, then you can, at the same time, from that one plot, you can determine what the standard enthalpy is for that reaction and the standard entropy for that reaction. Okay, that's the Van Hoff equation. And that's what it looks like. Somebody's data is there. I don't know whose it is. The authors of the textbook probably stole it from somewhere, from a research paper. Okay. Achieving the maximum work available from a spontaneous process can occur only via a hypothetical pathway. That's the one where the incremental change is reversible. Any real pathway wastes energy. That means all real processes are irreversible. All right, I like this. Oh, got that already? Okay. I like this description of the laws of thermodynamics. True but humorous. That. All right. The first law of thermodynamics, remember what? Total energy in the universe is constant. Delta E = 0. That means you can't win. Right? You can't make more energy, you can't destroy energy. You can't win, but you might be able to break even. You can't get more energy out of a system than you put in, so that means you're even. However, the second law comes along and says you can't even break even, right? Because you're going to lose some of that energy to disorder, right? Minus T delta S. Any transfer of energy will result in some waste. Unless you have access to absolute zero. And you don't even have that in outer space, right? What's the average Kelvin temperature of space? Think background radiation. The background radiation, and I can't remember the scientists who discovered this. They did it in New Jersey with a radio telescope. They discovered the background radiation in the universe. It's at an average temperature of 4K. Right? So you can't even get to absolute zero in space. That means you can't break even. The third law says you can't even get out of the game, right? Because you cannot achieve absolute zero. So the moral of the story is whenever you use energy to do work, you degrade its usefulness. You take it down to this level, right? You can't get that work back. It's gone, right? So you have to work from here down to another level. Now that's for the whole universe. On a local, isolated level, we can couple these systems and surroundings and achieve some useful work from lower energy situations. But it takes some ingenuity. That's it for thermodynamics. We'll next Monday, the reason I gave you both versions, right? You got two versions of the review document is because my review encompasses some from one and some from the other. So just as always, go through there, and if you're limited on time, just work one of them, and if you come across one that's like it, skip it. Mark it to come back to it if you have the time, right? Try to get experience with all unique problems, and then come back and try to be bored later.
So, we don't have lab, like the last lab was the last.
That was it. Let me see. When is this last one due? That's always a question that's asked.
I haven't got the data from my lab partner, so
Oh.
it might be a week later or something.
Oh, complex ion, that was the last. Okay, I got a due date of the 22nd of April. Now, let me look at the, see, this is a better. So. Okay. Now, actually, 22nd will be next week. I think 29th of April will be okay. Yeah, that would give me enough time to grade them. That's all I'm concerned with. I want to have time to grade them, give you my due consideration, and then everybody be happy. Registrar be happy because I can get my grades.
Oh, wow, this semester is coming to an end.
Yeah, it's just about over. All right, and then you move on to bigger and better things. Hopefully, right? Okay, we're going to end today.